Alright, so today I'm going to be explaining this important paper with the title Graph Neural Networks with Heterophily. This AAAI paper in 2021. Graph neural networks have proven to be useful for many different practical applications. However, many existing GNNs have implicitly assumed homophily among nodes connected in the graph, and therefore have largely overlooked the important setting of heterophily, where most connected nodes are from different classes. In this work, we propose a novel framework called CPGNN that generalizes GNNs for graphs with either a homophily or heterophily. The proposed framework incorporates an interpretable compatibility matrix for modeling the heterophily and homophily levels in the graph, which can be learned in an end-to-end fashion, enabling it to go beyond the assumption of strong homophily. Theoretically, we show that replacing the compatibility matrix in our framework with the identity reduces to GCN. Our extensive experiments demonstrate the effectiveness of our approach in more realistic and challenging experimental settings with significantly less training data compared to previous works. This is the general pipeline of the proposed framework with K propagation layers. We use a graph with mixed homophily and heterophily with node colors representing class labels. Nodes in green show strong homophily, while nodes in orange and purple show strong heterophily. CPGNN framework first generates prior belief estimations using an off-the-shelf neural network classifier, which utilizes node features if available. The prior beliefs are then propagated within their neighborhoods, guided by the learned compatibility matrix, and each node aggregates beliefs sent from its neighbors to update its own beliefs. So again, in this paper, they introduce this homophily ratio. So in the denominator, you have E transpose DE, where D is a diagonal of Cij. But in the denominator, we have C transpose C, and C sub ij is defined here. So it's good for measuring the overall homophily level in the graph. And we have edge in this interval. Graphs with edge closer to 1 tend to have more edges connected node with the same graph, or a stronger homophily. On the other hand, graphs with edge closer to 0 have more edges connecting nodes in different classes, or a stronger heterophily. Now they define compatibility matrix. And this is just the Hadamard, which is element-wise division, and E is a V by V all ones matrix. So we have two stages in this framework. First, we have prior belief estimation. Then we have compatibility guided propagation. In estimation, the goal of the first step is to estimate per node via prior belief of its class label from the node features. This separate explicit prior belief estimation stage enables the use of any off-the-shelf neural network classifier as the estimator, and thus can accommodate different types of node features. In this work, we consider the following models as the estimators. You could either use MLP, multi-layer perceptron. Specifically, the case layer of MLP can be formulated like this. Now here W is the learned parameters, and we initialize it by X. So this is one kind of estimator model. The other kind of estimator model is GCN Chebyshev, which is based on second order Chebyshev polynomial. Now the output of the final layer of the estimator then the prior belief can be estimated, can be given as this. And so the second stage is compatibility guided, that we propagate the prior beliefs of node within their neighborhoods using a parameterized end-to-end trainable compatibility matrix H, this H bar. So we parameterize H bar to replace weight matrix in the traditional GNN. So we similarly denote B as the final belief for node V. And the training is here. First, we have pre-training of prior belief estimator. We pre-train it so that H bar can be better initialized with informative prior beliefs. The pre-training process aims to minimize the loss function, where H corresponds to cross entropy. We empirically found that initializing the parameters with an estimation of known compatibility matrix can lead to better performance. So H bar, the estimation is just the unknown compatibility matrix. We use Sinkhorn Hinop. In this paper, they use that algorithm, which is for 1967. And it ensures that H hat is doubly stochastic. To ensure the rows of H bar remain centered around 0 through the training process, they adopt this regularization. And finally, we obtain the loss function of this model. So first we have the cross entropy. This is the cross entropy loss function. Then we have L2 regularization. And finally, a regularization term keeps H bar centered around 0. Unlike the hard-to-interpret weight matrix W in classic GNNs, parameter H bar can be easily understood. It captures probability that node pairs in specific classes connect with each other. Through an inverse of the initialization process, we can obtain an estimation of the compatibility matrix after training from learned parameter H bar. So this is data for heterophilous graphs and homophilous graphs.